We already know how to make spiders silk. We've decoded the proteins, replicated the chemistry, and spun fibers that rival steel. But we still can't do this. And I wanted to understand why, because if we already have the ingredients and the chemistry figured out, then why is there such a massive gap between lab-grown thread and a wrist-mounted ballistic cable that can stop a moving truck? Here's what didn't make sense to me initially. In the 1880s, a French missionary in Madagascar built a guillotine-style machine that could extract silk from 24 spiders at once. He was extracting almost 50 meters of thread per spider. But then the project collapsed. Not because of the silk or the machines, but because it required around 25,000 spiders to make a single ounce of fabric. But modern biotech can manufacture complex proteins from genetically modified bacteria and yeast. So if this isn't a supply issue, where does the system actually break? It turns out the real issue was the manufacturing process itself. A spider's silk duct is around 10 micrometers wide, about the size of a red blood cell. We manufacture computer chips at nanoscales. A 10 micrometer channel shouldn't be a technological barrier, and it's not. But replicating what happens inside that duct at the speed needed for a web shooter, that's where the engineering gets tricky. So what's actually going on? Spider silk isn't stored as a thread inside the spider, it's stored as a liquid protein solution called silk dope. As that liquid is squeezed through a 10 micrometer duct, the tight confinement combined with the shear stress aligns the proteins, locking them into crystal-like structures. Beta sheet crystals, the structures that give silk its strength, don't form instantly. A spider pulls silk at a few centimeters per second, giving proteins just enough time to form and lock into place. But at ballistic speeds, the proteins wouldn't get enough time or the right conditions to form correctly and snap into that ordered structure. Instead of a clean, high-performance fiber, you get something closer to a messy spray of half-assembled silk. The only way to buy those proteins more time is to make the reaction happen faster. You do that by stripping out the water so the proteins are packed tighter and find each other faster. But with synthetic dope, if you push the concentration too high, the chemistry turns on you. The hydrophobic regions of the proteins start clumping together like drops of oil in water. Instead of a smooth, fast-acting liquid, you end up with a biological sludge that ruins the material before it even reaches the nozzle. So if it's impossible to spin the silk live during the shot, what if it's already fully formed and stored in the cartridge as a pre-spun solid cable? That solves the chemistry, but it raises an immediate question about storage capacity. I did the math. If we assume the average human weighs around 60 kilos, that's nearly 600 newtons of tension in the rope. Spider silk has a tensile strength of 1 gigapascal, meaning the minimum cross-sectional area of the thread would need to be 0.6 square millimeters. If we fire 40 10-meter shots per fight, that's 400 meters of cable. This would require almost 0.25 liters of storage space if the rope were packed perfectly tightly. But that's the absolute minimum for a body standing perfectly still. The second you start to swing, the G-forces would multiply that load at least 2 to 3 times over, which means the real minimum storage requirement jumps to nearly 3/4 of a litre. A single shooter looks like it holds 100 millilitres at most, so even at our impossible perfectly packed minimum, we're already over capacity by a factor of 7. The real magic of Spider-Man silk is that it somehow bypasses every chemical and physical barrier that holds back our most high-performance synthetic versions, all while fitting into a compact delivery system. Our current progress shows exactly how far off we are. We've managed to produce genetically modified silk that matches the strength of natural spider silk, but the storage math for a wearable wrist-mounted device doesn't add up. And we've replicated the process of squeezing dope through micrometer-sized ducts, but we can't scale it to match the speed needed for a web shooter. Unless we can transition from these bulky, sluggish configurations to portable high-velocity delivery systems, the technology remains confined to the lab and in the realms of science fiction.